Hello, this is Dr. Bahauddin Abdullah, and this is the second part of section 11.6, and it would be about the ratio and the root tests. This is the ratio test. It says that if limit absolute value of an plus 1 over an is less than 1, then the series summation an is absolutely convergent. And if this limit is greater than 1 or infinity, then the series is divergent. And if the limit is 1, then the test is inconclusive. It doesn't give any information, and we have to use other tests. So let us try two examples. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. Let us first look at this series. Whenever you have n factorial or n to power n or exponential function, immediately think of the ratio test. It is very powerful in these cases. So this is an, and to find an plus 1, you just replace each n by n plus 1. So you will have n plus 1 factorial, and here instead of n you will have n plus 1. Let us simplify this one. N plus 1 to the power 2 expand, so it would be n squared plus 2n plus 1. Now let us divide an plus 1 by an. So when you divide an plus 1 by an, there is no need for the absolute value because all of these are positive. This is the division. I wrote it like this because I don't want to have complex fractions. This division will be changed to a multiplication product with the reciprocal. And now you can see that n plus 1 factorial is n plus 1 times n factorial, and this one you can write it 2n squared times 2 to the power 2n plus 1, because if you add the powers you go back to this. Why? Because now you see that these two cancels and n factorial cancels with n factorial, and you get this one. You can rewrite this if you like. This is 2 to the power 1 times 2 to the power 2n, and 2 to the power 2n is 2 to the power 2 all to the power n, so it's 4 to the power n. So in fact you can write it 2 times 4 to the power n over n plus 1. If you take the limit to infinity, it would be, when n goes to infinity, it would be infinity over infinity. So we need to use L'Hopital's rule. So let us write it as a function and then find the limit. It is infinity over infinity, so we need to take the derivative of the numerator and the derivative of the denominator. The derivative of the denominator is 1, and this is a constant. The derivative of 4 to the power x, as we know, is 4 to the power x times ln 4. So we will have this limit. And now if you take x to infinity, you will have 4 to the power infinity, and all of the other are numbers, constants, so it is infinity. Using the ratio test, the limit is infinity, so the series is divergent by the ratio test. Second example, we will have a look to this series. You have again factorial and n to the power n, so the best test to use is the ratio test. This is an plus 1 would be replacing each n by n plus 1, so you'll have n plus 1 to the power n plus 1 and n plus 1 factorial. Now divide an plus 1 by an. Change the division into multiplication, and again remember that n plus 1 factorial is n plus 1 times n factorial, and you can rewrite this as n plus 1 to the power n times n plus 1. Now you can see that these two cancels and n factorial cancels with n factorial, and you get n to the power n over n plus 1 to the power n. Again it's infinity over infinity, but we have something to use. We have this limit which we studied in calculus 1. If you take n to infinity, this would be 0. It would be 1 to the power infinity. And when you have 1 to the power infinity, you call this y, and you apply ln to both sides to bring n down, and then you will find that the limit is 1, and then you raise it to the power e, to the base e, and then you will find that this limit is e. You can use this as a fact. Limit 1 plus 1 over n to the power n when n goes to infinity is e. Notice that if you add these two, you get n plus 1 over n. So also you can write it like this. What if you have n over n plus 1? That's the reciprocal of this. So you will get the reciprocal of this. So the limit of this is 1 over e. And this is exactly this one. So in fact, the limit of an plus 1 over an is 1 over e. And 1 over e is less than 1. So using the ratio test, the series is absolutely convergent. The second test is the root test. It's very similar, but here we deal with roots instead of ratios. The nth root, and this works when you have a series to the power n. Terms raised to the power n, so n will cancel with this n, and it would be very easy to find the limit. Again, if this limit is less than 1, the series is absolutely convergent. If it is greater than 1 or infinity, the series is divergent. If it is 1, the test is inconclusive. Use other tests. So let us see this example. Let us try to find the limit of the nth root of absolute value of an. Well, the negative sign will disappear because of the absolute value. And you will have nth root of 2 over n. 2 to the power n over n to the power n. You can write it 2 over n all to the power n to cancel n with n. And you get limit 2 over n when n goes to infinity, which is 0. That's less than 1. So the series is absolutely convergent by the root test. Good luck.